Anna John, good morning.
Hello,
How are you?
good.
Good. What did you do today, yesterday?
Study.
You studied.
It's 10 o'clock.
What did you study? I saw you didn't, excuse me, you didn't submit some assignments.
I forgot I submitting the morning.
I'll give you 0, okay, for any assignment you didn't submit.
Okay.
Bill, welcome, Bill.
Hello.
Hello. How are you? Um, okay. I'm going to go straight to what we should be doing today. The aim of our classes is just to derive the formulas, okay? Because the work you are doing in this chapter is just about using those formulas that we derive. And so if I derive them and then you use them to just solve a few problems is enough. The most important thing is to know how to get those formulas when you need them. Huh? Okay. So today we are looking at how to find the surface area of revolution using integration. I think when you guys studied P1, you did a similar kind of a thing. If you have, say, your XY plane, and let's say you have a function. Let's make this function like this. This is the function y equal f of x. And we take this function and we rotate it 360 degrees about the x-axis. Then we can say that this function, when rotated, we can sketch it to look something like this. So you rotate it about the x-axis 360 degrees. So it will form this figure. Our aim is to find the area of the surface of the object that we have. This area here. Our aim is to find the area, not volume. I know that when you guys were studying P1, you had a formula for looking for the volume, which you should remember now. Okay. Drawing from the work that we had last time, we remember last time that if you want to find the length here, if this length is ds, for example, and then we revolve the length through about the x-axis. So we revolve dx through the x-axis. We need to find this small area here. What will be this small area? First, last time we saw that gs squared was equal to dx squared plus dy squared. And that gave us ds as square root of 1 plus dy over dx squared dx, right? That's what we saw last time. And if your function is given in terms of t, that's a parametric function, we saw that ds, since ds over dt squared equal dx over dt squared plus that will give us square root of dx over dt squared plus dy on dt squared times dt. So that is our ds for this small part here. Okay. We know that this height, the radius of this circular portion will be y, your f of x at this point, right? And so to find this area, we can cut this area and it will form a rectangle. It will form a figure like this, where this side is ds and this side is, it is the circumference of the circle. So it's 2 pi y. So the area dA, the small area that you have here, dA will be 2 pi y ds, right? That will give us dA equal 2 pi y, ds is square root of 1 plus dy on dx squared dx, giving us, we can now integrate to find the whole area. You integrate dA, you'll get A should be equal to integral of 2 pi y square root of 1 plus dy over dx squared dx. You can integrate from x1 to x2. And if your equation is given in parametric form, you can just put the parametric part. ds here becomes that, and that will just give you your A to be integral from t1 to t2 of 2 pi y square root of dx over dt squared plus dy on dt squared dt. So these are the two formulas. Again, I don't recommend memorizing formulas, these formulas. But if you would have a question that needs you to use them, you can easily derive them. All right? I will not do any example. There are some examples in the course on my website, which you can check out. But another thing, maybe when you took that function, y equal f of x, instead of revolving it about the x-axis, you decided to revolve it about the y-axis. To get something like this on that side. This may be a very bad sketch for this function, but you revolved it about the y-axis. Then we can show, using the same method, we can show that your area of revolution will be integral from x1 to x2 of 2 pi x square root of 1 plus dy on dx squared dx. So the y here, the only difference is that the y here changes to x. And you can know the reason when you take a small part of this area, ds, then the radius of that small part is x. So when you cut it into a rectangle, you will have this, and this is x. This is 2 pi x, and this is ds. So the only difference is that this one will change to, instead of 2 pi y, you have 2 pi x. And if it's in parametric form, you have something like integral from t1 to t2 of 2 pi x square root of dx on dt squared plus dy on dt squared dt. Okay. Are there any questions? Does anybody have a question here? Finally, we have 6 students already. Oh, 5 students already. Is there a question? No question. For today, you have some pretty good examples in your book. You only need to go to your book. You will solve question 2. question 7 and question 8, I think so. No, question 8 has been solved already. I think question 5, question 2, question 5, and question 7. It involves surface area of revolution. If you go to the course, if you go to the course on my website, lesson 5 has 2 videos where some 2 good examples have been solved. It's actually 1 good example has been solved with those 2 formulas, if you would like to look at them. Otherwise, if you are not looking at them, just solve these questions and submit today. Okay? We are not going to have any math class. During math class, you guys will be solving some problems. You'll solve the rest of the end of chapter exercises. Okay? I'll end the class now. Thank you guys for coming.